Good afternoon, folks. This is going to be our hybrid content for this week concerning the brain. We are picking up where we left off in our lesson with this, having already discussed the structure of the brain anatomically. We're now going to be taking a look at some important cognitive functions of the higher brain. If you were following along with my handout on Blackboard, you might want to keep my handout on brain structure and function handy for some important terminology as we proceed. And what I want to be taking a look at here today is looking at some of the broad functions of the forebrain dealing with what we call cognition. And cognition is a general term referring to the conscious activities of what is often called the higher brain, the forebrain. That is, the activities that are for the most part, under your conscious direction and control, as opposed to the autonomic functions that we discussed that are largely managed by the midbrain and the hindbrain. Under the heading of cognition, we're including a very large assortment of mental activities that we broadly think of as thinking. Your internal narrative, your perception and awareness of your environment and your own bodily sensations, your knowledge and memory, your ability to draw upon past experience and learning, your ability to learn and derive new knowledge from experience, your sense of judgments, your ability to plan and have foresight and to think ahead about activities, your ability to process knowledge about current experiences, your ability to make comparisons between pieces of information that you are experiencing right now and previous knowledge that you've already obtained, your ability to speak and to formulate words and thoughts. All of these things fall under the general heading of cognition, and most of your brain is dedicated to this kind of activity. It is estimated that approximately 75% of the processing area of your brain in the cerebrum consists of what we call cognitive association areas. And that means parts of the cerebrum that are dedicated to essentially taking pieces of information, joining them together. Oh, hold on one moment, folks. I will be with you in just 1 second. I just came to a realization about my environment that I didn't realize was going on. 1 second. Oh, hello, Nova. 1 second. I'm so sorry. Come here, look at me. Everybody, this is Nova. I didn't realize Nova was in the room. Say hi, Nova. Nova is in the room. The door was closed. I didn't know she was in here with me. Okay. I'm going to put you down, Nova, and let you out. My apologies, girl. So. Okay. So, yeah, she was scratching at the door trying to get out. I had no idea she was in here. Okay. Anyhow, though, so about 75% of the cerebrum is dedicated to processing data, linking up current sensory experience with old knowledge, previously obtained learning and information, linking together current pieces of information with each other in order to assemble a comprehensive understanding of what is going on in your present environment and linking it with your existing knowledge to gain a full picture of what is happening and enable you to arrive at decisions necessary for the body to maintain homeostasis, to make internal and external changes needed to react to your environments. Now, different thought processes are happening in different regions of the brain. Not every part of the brain is involved in every kind of cognitive activity. As we saw when we were discussing the different lobes of the cerebrum, different regions of the brain engage in different kinds of processing. That we're, for example, doing language comprehension in the forebrain. We are doing sensory processing largely in the parietal or temporal or occipital lobes, depending on what kind of sensory data is coming in, that we have different regions that are handling different aspects of cognition. And a lot of times, any given thought is being assembled by putting together data from several different regions to link that information via tracts of white matter. We have learned through studying brain pathology, damage to specific regions of the brain lesions or tumors that have impaired the ability of one region of the brain or another to engage in its normal activities, a lot more about what kinds of cognitive activities specific brain regions engage in. And if you have damage to a particular region of the brain due to a stroke, due to an injury, due to a brain lesion or tumor, you can find yourselves having impairments in certain specific kinds of activities. For example, damage to Broca's or Wernicke's areas of the brain can result in what we call aphasia, which is limits in your ability to effectively use language. Even if you can understand it, you may not be able to form words properly. Damage to the parietal lobe of the brain can sometimes lead to a fascinating disorder called contralateral neglect syndrome, in which you are aware of only one portion of the body, and the other half of the body is kind of something you're not paying attention to. I mentioned the situation of left-right brain dominance, that we all have a dominant lobe of the brain. And I mentioned that there used to be a procedure that was more commonly done in the past, but very rarely done in modern times, where the corpus callosum connecting the left and right hemispheres of the brain would occasionally in past times be severed as a way of dealing with intractable epileptic seizures. When that happens and the left and right hemispheres of the brain stop communicating, they effectively begin operating as their own cognitive centers. And you can end up with what we call contralateral neglect syndrome, where literally the left half of the brain does not know what the right half is doing. And you can have a situation where someone's right hand may be acting without them being aware that they are doing it, that the left half of the brain literally does not know what the right side of the brain is doing, and one side of the brain or the other may be taking actions the other side does not know is happening. Psychologists call this alien hand syndrome, where you literally, one of your hands might be taking an action that you are not consciously aware that is taking. Or you might find a less severe version of this, in which you have a harder time, say, coordinating the actions of both hands at once. Failure to communicate between the two hemispheres of the brain due to damage to the corpus callosum can also lead to processing problems. There's a famous example in psychology of an individual in the 1960s who had the corpus callosum cut as a way of dealing with intractable seizures, and discovered that he could not process all forms of data effectively when the two halves of his brain could not communicate with each other. That if he covered his left eye and looked at an object, he could tell you, oh, that object is a chair. But when he was asked what the function of that object was, he could not explain it. Covering his right eye and looking at the same object, he could tell you, oh, I sit on that object. I have one by my desk at home. But he could not give you the name of the object. He could not call it a chair. He could only do those things when both eyes were acting at once. If you have lesions on the temporal lobe of the brain, that seems to interfere with our ability to link language and names to objects. It can lead to problems like agnosia, in which you forget the names of objects, or prosopagnosia, in which you recognize, you know people, but you cannot recognize their faces. And even someone who you've known for your whole life, you can't identify them by their face. I have a friend who has prosopagnosia due to a temporal lobe defect. And anytime I see him, I say to him, "Hi, Bryce, it's Adam." Because even though I've known him for decades, he does not recognize my face because of a problem with the temporal lobe of his brain. And he knows me well, we're great friends. It's just my face does not register for him because no one's face registers for him. Now, I want to mention in particular, last class I talked about the frontal region of the brain and an area called the prefrontal cortex, which is useful for planning actions. It's part of our ability to plan and execute actions, to form judgments about appropriate actions, and is particularly useful for judging appropriate emotional and social reactions. And it's a very important area of the brain for we as humans living in social contexts. We are evolved as a social animal. Now, one interesting thing about this is that if that region of the brain right behind the forehead gets damaged, it can interfere with our ability to properly judge those kinds of reactions and behaviors. Some of you who have taken a psychology class might be aware of the tragic case of a man from the late 19th century named Phineas Gage. Phineas Gage is often cited in psychology classes in pointing out how much of our personality is actually biologically encoded. Because Phineas Gage was a railroad worker who had a tragic accident happen when they were blasting out a tunnel, using dynamite, to blast through a mountainside. And he was packing down blasting powder with an iron rod like they used to use back in the 19th century to prepare for the blasting out of tunnels, and it went off prematurely, and the iron rod in his hand shot up, went through his eye socket into his brain, and came out the top of his skull. Believe it or not, the man survived this process, got up after lying unconscious on the ground for about 15 minutes, and supposedly walked into the nearby village with this iron rod sticking out of his face, strolled into the office of the astonished local doctor and said, "Hey, doc, you're about to earn your $5 for today." Because apparently doctors were not paid all that well back then. And Gage survived this, lost an eye, fairly obviously, but a portion of the prefrontal cortex of his brain was destroyed. And Gage has become kind of a case study in all of this because in the weeks and months after his injury, he underwent a remarkable personality change. People who knew him before his injury knew Phineas Gage as a kindly, loving man, went to church every Sunday, loved kids, loved animals, always willing to lend a helping hand to his neighbors. Real nice, upstanding, solid citizen kind of guy. Following his injury, Gage became mean, nasty, picked fights with everyone, cursed people out, flew off the handle at the slightest provocation. He would whip out his penis and pee in the middle of the street because he didn't understand why that was inappropriate. He basically lost all sense of what was inappropriate social behavior and all ability to emotionally regulate. Couldn't hold down a job anymore, lost most of his family and friends, basically ended up dying a drunk alcoholic in the gutters about 10 years later, after briefly holding down a career as a prize fighter, and exhibiting himself as a circus freak with the iron rod that had been blasted through his own head. Really tragic case, but it also shows what happens when the portion of your brain that helps regulate a big part of your personality gets destroyed. And it's a chilling reminder that a big part of what we think of as our own self is not just some ephemeral thing inside of us, but it's hard-coded in the physical structures of our brain itself. Now, we could spend an entire course talking about cognitive mechanisms, and psychology classes go into this to a certain extent. Neurology classes go into this to a certain extent. I'm not going to go super deep into this. I wanted to kind of give you an introduction to a sense of, the lateralization of all of this and how much our brain is managing all of this. But a thing I do want to talk about is consciousness and our conscious awareness of our environment and how we can actually measure that in terms of the electrical activity in our brains. Because your brain at the end of the day is an electrical machine, folks. Your brain is receiving electrical impulses from nerves, carry data from our senses. It is powerfully electrically active at all times, processing that data, sending electrical impulses from one region to another. It is sending electrical impulses out to direct the body. The human body is ultimately electrically powered. Your brain, I love this little statistic, draws about the same amount of electrical power as a 60-watt light bulb. And we can track what is going on in your brain to a certain extent by tracking the electrical changes happening in different brain regions. And we can measure electrical changes across the surface of the cerebral cortex to find out what brain regions are more or less active at a given time, and even how active they are, depending on the frequency of electrical activity coming from a given brain region at a given time. Those rhythmic electrical changes coming from the brain as its activities proceed are called brain waves, which sounds like a science fiction term, but it's a very real thing and can be measured with a device called an electroencephalogram, or EEG for shorts. And we can put electrodes on you and actually track the electrical activity in different regions of your brain. With more precise scanning technologies, we can measure this in very minute detail. We can track exactly which sub-regions of lobes of the brain, even which gyri are generating which wavelengths at what times, and get very precise measurements of precisely what regions of the brain are engaged when you are doing specific activities, like doing a math problem, reading a book, looking at a picture of something pretty. What's happening in your brain that's different when you are, say, watching a scary movie versus watching a funny movie? What's going on in your brain that's different when you are thinking about a memory of your grandma that you loved versus thinking about the day your grandma died? And we can measure all of this and think about it and learn things about precisely how the brain does what it does and what regions are engaged. And this kind of technology is letting us map the brain to an astonishingly accurate degree. But more generally, more broadly, we can talk about levels of conscious activity by the broad brainwave activity being emanated and how intense those brain waves are. Now, for those of you who don't know much about electrical activity, generally speaking, electrical waves are measured in hertz. Capital H, little z is the unit of brainwave frequency. Hertz, measure frequency in general, hertz. And we can track them at levels of intensity, and we can see where in the brain they're coming from and get a pretty good sense of how consciously active you are and what kind of activity the brain is engaging in. And by tracking brain waves, we can learn about your state of consciousness. Broadly speaking, we divide brain waves into 5 categories of intensity, from highest to lowest, that will tell us things about your state of conscious activity. So let's go through those categories. Now, the most intense waves emanated by the human brain are called gamma waves. And when you write gamma waves, you can either write it out. I'm going to put this in the chat. I hope you can all see the chat for this right now. If you're watching the video, I don't know if that's going to appear. Actually, I'm going to screen share with you all for a moment. I'm going to show you all, and this is straight out of the notes for today. So if you were following along with my notes from the Blackboard site, you can see this all exactly. But I'm going to share so you can see what I'm talking about. Okay, so the most intense brain waves are gamma waves. And you can write out gamma, or you can use the Greek letter gamma, which looks kind of like a letter Y, to represent them. And as you can see, gamma waves have a frequency of between 40 and 120 hertz on average. Gamma waves originate primarily from well, they can be found anywhere in the forebrain, all over the forebrain when they're happening. There's not a single spot. You tend to see them most intensely in the frontal lobe, but anywhere in the forebrain. When we see gamma waves coming from your brain, that tells us you are locked in. That is indicative of you're focused, you're paying attention, you're thinking hard, you are concentrating, your brain is really in the moment, you are paying attention, you're thinking hard about stuff. This tells us that you are trying to actively recall information from your memories and your learning. This tells us you are really trying to concentrate intently on something. It is also present when your brain is doing a thing called perceptual grouping. Perceptual grouping is when you are trying to sort things into patterns. When your brain is saying, okay, how do these things go together? When your brain is trying to uh, determine patterns of information, whether that means it's looking for a pattern in a group of numbers, whether that means it's determining, okay, how do these objects go together? Are they all blue? Are these objects all made of the same kind of material? Anytime your brain is looking for a pattern of any kind, that's perceptual grouping. I should point out, not all gamma wave activity is good. If we see random spiky gamma waves that are not associated with intense concentration, that is sometimes the thing associated with an epileptic seizure. When somebody is having a seizure, their EEG will show random, highly jagged, unpredictable gamma activity. But for the most part, when we're looking at gamma waves, that just means really focused, highly attentive brain activity. Gamma activity is strongly reduced in people who are experiencing schizophrenia and in people who are experiencing Alzheimer's and other forms of dementia. They have a hard time getting their brain into that highly focused, locked-in state. Now, let's take it down a notch. Right now, if you are paying attention to this lesson, if I had an EEG on you, there's a good chance your brain would mostly be giving off beta waves. And as you can see, we can write out beta, B-E-T-A, or we can use the Greek letter beta, which is similar to a B, to represent beta waves. Typical frequency of beta waves is between 14 and 40 hertz. Beta waves mostly originate from the parietal lobe of the brain, which is not surprising because the parietal lobe is most strongly associated with sensory processing, and beta waves are most present when your brain is active, being stimulated, and you are aware of the environment around you. Beta waves are indicative of essentially normal, everyday conscious activity. You are awake, you are aware of the world around you, you are paying attention, you're receiving conscious sensory stimulus, you're engaged in things that are happening. Basically, this is a normal state of everyday awake awareness, doing stuff with the world around you kind of activity. Normal conscious activity. This is beta activity. So you're alive, you're awake, you're walking around, you're thinking about stuff, you're doing things. You're not that super focused, locked in that we associate with gamma activity. Your brain is giving off beta waves. We'll have occasional spikes into gamma activity whenever we see you really paying sharp attention to something. But you're not always that focused, are you? Maybe you're in a class that's a lot more boring than the one you're in right now, because my class is exciting, right? But maybe you're in one of those boring classes that you don't want to be in. Or maybe you're in a boring meeting and your boss is droning on and on, and you're not really there and you're disengaging. And your brain is going somewhere else. You close your eyes. You start to float away. Yeah, this is better. Or maybe you just had lunch. You're sitting back in your chair and you don't have anywhere to be for a while. And you just chill. And you disconnect a little bit. And our brains take it down a notch. And then I would start to see alpha waves. You can write out alpha, or you can use the Greek lowercase letter a for alpha. Alpha waves have a frequency of 9 to 14 hertz, and they mostly originate from the occipital lobe of the brain. Remember, the occipital lobe is primarily associated with visual stimulus, and you tend to give off occipital lobe alpha waves when your eyes are closed and visual stimuli are not really coming in. Alpha waves happen when you are awake, but you are resting. You're relaxed. Your eyes close. Your mind is wandering. You're drifting, starting to daydream. You're disengaged from the world around you. You're not really paying attention to the outside world. Stimuli from your senses, things happening around you are kind of fading away. You're off in your own little place inside your head. The alpha state is that place that you end up in where you're not asleep, but you're kind of starting to get closer to sleep. Starting to drift off. You're in that little twilight place that you end up in right before you fall asleep. But you're definitely you're there, you're dimly aware of the world around you, but you're definitely not engaged in it. It is possible to enter an alpha state when your eyes are open, but mostly you tend to close your eyes when you get into this alpha state because the more visual stimulus you're getting, the less your occipital lobe has processing power for this kind of thing. Alpha waves are absent when you are in a deeper state of sleep. They go away very quickly when you are experiencing stronger sensory stimulus or when your brain is engaging in any kind of mentally stimulating task. When anything is demanded of you mentally and you have to really engage your conscious thinking, you slip out of that alpha state pretty quickly. So this is that in-between kind of place. This is the place, by the way, if you've ever been hypnotized, a hypnotist will guide you down into that semi-conscious, highly suggestible place. That is the alpha states. But you know what? Let's keep going down. And let's get down into theta waves, which have an average frequency of 4 to 7 hertz. I know we go 9 to 14. I guess 8 hertz is kind of a alpha theta kind of gray area there. Theta can be written out, or you can use the Greek letter theta, which looks like a 0 with a bar across it. When you are in the theta states, this is the state where you're usually asleep. So-called stage 2 sleep, normal sleep, is the state of theta activity. When you are in REM sleep, we'll talk about that in a few minutes, theta waves are dominant. When you are in the transition between sleep and waking up, your brain will emanate theta waves. Theta waves are mostly emanated by the hippocampus. We see them most strongly coming from the hippocampus, which is that part of the brain which you might recall is involved in memory consolidation, the part where we transmit memories from short-term to long-term. And this is part of our hypothesis that one of the main functions of sleep is that sleep is the time when your brain is processing memory. And when your brain is converting memories from short-term into long-term storage. And that seems to be one of the main functions of sleep. And that seems to be why theta activity is dominant during REM sleep and stage 2 sleep. It is interesting that we will see theta waves occasionally in people who are awake. Theta activity is present in conscious awake people in a few circumstances. Theta activity is seen when you are doing repetitive tasks. If you are mentally disengaged, but you're doing a repetitive task over and over and over again, your brain is not being stimulated by any outside thing, and you're just doing the same task over again and over again and over again. Your brain can slip into a theta state even when you are technically awake. This is often documented in factory workers, people who are working on assembly lines, manually performing the same physical job over and over and over, repetitively for hours and hours, will sometimes slip into a theta state. In your day-to-day life, have you ever been doing the same physical task over and over and over again for prolonged periods of time, and somebody jolts you out of it, and you suddenly feel a jolt, like, oh, what just happened? What just happened? You were probably in a theta state for a while. Experience some of you may have had. If you've ever been driving for a long period of time on an open highway where there were no stop signs and no pauses, and it was just the open road for long stretches of time for hours and hours, and you found yourself, as people sometimes put it, being hypnotized by the road, and you kind of just everything sort of blurred out and you weren't really paying attention, that getting kind of hypnotized by the road condition, that is a theta state. And that can be really dangerous, which is why it's a real good idea if you're doing that long highway road drive to have something to pay attention to, something to jolt your brain out of it, something to keep you from getting lulled into that hypnotic sleep-like state when you are driving. We will also find theta waves, interestingly enough, present in awake adults who are in states of high creativity. People who are conscious, but they are doing something really creative. They're writing, they're composing music, they're dancing. Their creative parts of their brain are really engaged. Theta waves will be present even when they're awake, and we do not know what this means. And finally, young children. Young children, pre-adolescent children. It turns out theta waves are the default state of their brains when they're wide awake. Kids' brains give off theta waves normally, even when they're wide awake and active. And we do not know what that means either. If you see them under any other circumstance in a conscious adult who is awake, active, and not doing something creative, that is usually indicative of some kind of brain injury or some kind of psychiatric disorder. Sometimes we'll find them associated or some kind of neurological disorder. Sometimes we'll see theta activity associated with things like schizoaffective disorders or parasomnia disorders, or sometimes with traumatic brain injuries. Now let's take it down even further. Let's get down to the slowest waves of all. They're literally called slow waves sometimes. Delta waves, which you can write out delta, or you can use the Greek lowercase letter delta you see here. They have a frequency below 4 hertz, 4 hertz or lower, to as low as 0.5 hertz. Slow waves. These are going to be primarily seen when you are in deep sleep, your very deepest stages of sleep that are hardest to wake up from. So this is when you were real deep down asleep. Slow waves or delta waves are the primary brain activity of wide awake infants. So babies and very young children up to the age of 5 will give off delta waves when they are wide awake. We do not know why. If you see delta waves in an adult that is awake, that is usually indicative of serious brain damage, or it is associated with a couple of certain specific psychological and neurological disorders. Delta waves in a conscious adult can be associated with severe depression, can be associated with narcolepsy, can be associated with Parkinson's disease, and can be associated with a family of things that we call parasomnias. Parasomnias are sleep disruptive conditions that look like you are awake. Things like talking in your sleep, sleepwalking, night terrors. People who are exhibiting those kinds of things where they're active when they are asleep, their brains are usually giving off delta waves. We have found that as you get older, your brain emits less delta waves and spends less time, notably in deep sleep. The production of delta waves seems to be specifically tied to the release of a couple of specific hormones, notably growth hormone, thyroid stimulating hormone, and a hormone called prolactin, all of which we're going to talk about when we talk about the endocrine system. They are mostly going to originate from the thalamus of the brain, with some observation of deeply sleep, slow waves coming across the upper surface of the cerebral cortex. Now, naturally, as we talk about these different kinds of waves and these states of consciousness, this brings us around to a really weird thing that we do. And that weird thing, which doesn't seem weird because we do it all the time, is a thing called sleep. Sleep is defined medically as periodic temporary unconsciousness that ends when you are stimulated. If it does not end when you are stimulated, the medical term for that is a coma. Now, I say it's weird because if you think about it from the standpoint of being an animal that has to survive in the world and the fact that humans originated as nomadic hunter-gatherers, surviving on the plains of Africa, the fact that we periodically go unconscious and cease to respond to the world around us for prolonged periods of time would seem like an adaptive failure because it makes us vulnerable and unaware of our environment for a prolonged period of time. Seems dangerous. Well, think about two things with that. One, we evolved as a social animal, which means that we are seldom alone, at least in our natural state, as it were. And two, think about the fact that this is likely only going to happen if we have some very important adaptive piece of significance that's going along with it. So we have to ask ourselves, what is sleep for? And it's something that almost all mammals do. Mammals, as it turns out, actually mammals universally do it. There are some species that don't. Many fish don't. Sharks don't sleep. But mammals universally need to sleep. Not all of them sleep at night. We are what is called a diurnal animal. When an animal is diurnal, that means that it sleeps by default at night and is awake by default during the day. Yes, you can reroute your schedule to be more night active with some efforts. Yes, there are some people who it seems have a circadian rhythm. That is a normal sleep pattern that is primarily tilted to be a little more active at night than during the day. Not all of us are on the exact same pattern. That seems to be an evolved instinct in our species where some people are always a little more awake. Once again, group evolved organisms, good for group survival. But as a whole, Homo sapiens as a species is diurnal, day active, as opposed to nocturnal, night active. The circadian rhythm, that is the day-night attunement, is pretty normal for primates. Most primates are day-active animals. It is largely governed by the hypothalamus of the brain. There is a region of the hypothalamus called the suprachiasmatic nucleus that controls the day-night attunement based on light coming in from the outside, and then signals certain glands, most notably the pineal gland, to release hormones like melatonin and serotonin that regulate our activity cycles. Why mammals need sleep is not clear. We know that all mammals, if deprived of sleep for too long, will die. We know that all mammals begin to have functional impairments if they are deprived of sleep for too long. Why this is, we don't really know. The primary hypothesis on the reason why sleep is necessary is for a thing called memory consolidation, the transfer of data from short-term memory to long-term memory. We think that basically your brain is using sleep as a time to process accumulated data, sort through it, discard what is not needed, figure out what is needed and how to associate it with previous learning, and then file it and store it properly. And we think basically that is what's happening during your dreaming. That's the primary hypothesis on what sleep and dreams are for. There's also reason to believe that sleep is when the body is engaging in a lot of quote-unquote housekeeping activities, engaging in repair, engaging in growth, engaging in basically routing resources to places that are difficult to take care of when that energy and when those resources are needed for conscious awake activities. But there is not one consistent, clear hypothesis and reason why sleep is happening. And for that reason, that matter, I should say, there's not one clear hypothesis on why sleep is needed in all mammals that doesn't explain why certain other animals, like a lot of fishes, don't need it. So, some things are not clearly resolved. But let's talk about what sleep looks like in you. And again, we're going to assume a normal sleep cycle. We're going to assume a sleep cycle that is not being disrupted by outside forces, not being disrupted by outside noises, not being disrupted by any kind of insomnia or anything like that. And it is worth pointing out that in the modern world, sleep disorders are very, very common. We have a chronic, persistent, and pervasive society-wide sleep problem. Why is this? A big part of it seems to do with the scheduling of modern life, that we have very tightly scheduled lives with a lot of disruptions, and many of us do not do a good job of prioritizing basic rest. A lot of it also has to do with electricity, namely that our ancestors lived in a world that was lit primarily by firelight and the sun. And that meant that when darkness came, the world was a lot darker for our ancestors, even 100, 150 years ago than it is now. And that meant that dark, sensitive hormones like melatonin that were sensitive to light levels in the environment and began inducing a state of rest and relaxation were much more easily activated. But from the time human beings learned how to trap lightning in glass and make electrical lights that illuminated the night, the difference between day and night has significantly blurred. And our circadian rhythms that were largely governed by light levels controlling hormone releases have become significantly disrupted. And we as a species are basically living in a society-wide disruption of our fundamental biological chemistry for the management of sleep. And honestly, the implications of that at a societal level, where literally everyone has their circadian rhythms disrupted by the very existence of electric lighting, are difficult to determine because we have a hard time setting up an experimental process by which we can test what it looks like when you don't have that going on, when literally our entire society looks like this. But it is not difficult to surmise that basically our entire culture is suffering from a sleep problem rooted in that exact issue. And the fact that many of us have sleep hygiene issues that come from the fact that we have these devices in our paws all the time and that we keep them in our paws up till the moment we are ready to close our eyes in bed. And therefore, we got bright lights on our faces until shortly before we're ready to say it's time to lie down is probably not helping. But I digress. Let's assume we've got a normal sleep pattern. Your initial stage of sleep, the way your brain is processing all this, is called stage 1 sleep, or N1. During N1, you're slowly drifting from sleep, or rather from wakefulness, I should say, into the sleep stage. During this stage, your breathing and your pulse are going to slow down. Muscular tension throughout your body will decline as that baseline muscle tone is going to gradually relax. Body core temperature will drop, and slowly but surely your body will become more and more relaxed. Your awareness of your environment will become less and less. During N1, alpha waves will dominate your brain activity as you will drift and become more and more disengaged from the world around you. Towards the end of N1, theta waves will begin to appear in your EEG. As little by little, you begin to slip into unconsciousness. You are relatively easy to awaken at this phase. N1 is the shallowest stage of sleep. You're still drifting at the edge of consciousness. Outside stimulus will knock you out of it pretty quickly. But assuming that nothing else disrupts you, most people will remain in M1 for 5 to 15 minutes. Now, from there, you will pass into stage 2, or N2 sleep. During N2, and this is just, you might say, normal sleep, the body is deeply relaxed. Slow breathing, slow pulse. You're just asleep. During this phase, your EEG activity, if we were monitoring it, would be primarily theta waves. However, what we would see on that EEG scanner would be occasional irregular spikes of higher brain activity called sleep spindles, where occasionally your EEG would spike up into beta or even momentary spikes of gamma activity for a few seconds or even as long as a minute or two at a time. Those sleep spindles are believed to be related to memory consolidation and learning, as your brain is processing the data that you took in during the day while you were awake and is now storing it and consolidating it. In the later stages of N2, the body becomes even more deeply relaxed and delta waves begin to appear in your EEG. For the average healthy adult, N2 sleep lasts for between 30 and 60 minutes. And then gradually you slide into stage 3, or N3 sleep. This is known as deep sleep. During deep sleep, the body is at its most relaxed. Your body temperature drops even more. Your pulse and breathing slow even more significantly than they did during N2. N3, you are very hard to wake up from. It takes some effort to wake you up from deep sleep. Delta waves dominate your EEG. And during this time, your autonomic nervous system will activate a lot of background activities that are minimally active when you are awake. The parasympathetic nervous system is dominant in this time. Growth hormone will be secreted. Your body will engage in intense cellular division for repair, growth, and healing. The immune system will become more active during this time for fighting any sort of infections or pathogens that you are dealing with. Your body basically is devoting a lot of its resources to processing nutrients, processing wastes, repairing damage, engaging in growth, engaging in healing, any sort of upkeep and cleanup tasks that require energy and resources that are not readily available when you're awake will be really intensely tended to during the deep sleep phase. Now, in an average healthy adult, deep sleep lasts for 20 to 40 minutes. But it is notable that as you get older, you will experience shorter cycles of deep sleep. And in some elderly individuals, N3 gets skipped altogether sometimes when you are sleeping. The shortening and sometimes absence of N3 sleep in older folks is a distinct contributor to reduced immunity, reduced healing, and reduced tissue repair in older adults. Why N3 sleep declines as we age is not known. Now, following N3, we move into stage 4. Now, the first 3 stages, N1, N2, N3, are often referred to as non-REM sleep or NREM sleep. And collectively, on average, NREM sleep tends to last for somewhere approaching 90 minutes. That's about the average of NREM sleep altogether, is about 90 minutes. Anywhere between, like at the short end, an MREM cycle might go for like 45 minutes, like an hour maybe, at the short end. At the long end of the cycle, NREM sleep might go for like 120 minutes, but about 90 minutes on average. Following your NREM phase, you move into stage 4, which is called REM sleep. REM stands for rapid eye movements because during REM, some interesting things happen to you. Your eyes begin fluttering very rapidly, hence rapid eye movements. During REM, it's sometimes called paradoxical sleep. Because when something is a paradox, that appears to be the opposite of what it is. Because during REM, anybody monitoring your vital signs would say, this person seems like they're awake. Because during REM, your breathing increases, your pulse increases to similar to or even higher than normal waking amounts. Your breathing often becomes irregular. Your EEG looks like the EEG of an awake person, showing irregular beta and even gamma activity. Men often gain an erection during REM sleep. Clitoral tissue can become erect as well. An interesting thing also happens during REM sleep. Your voluntary skeletal muscles are paralyzed. All these other bodily systems act like you are awake, but your skeletal muscles are paralyzed during REM. And the reason for this is because REM is when you experience most of your dreams. And this seems to be a biological mechanism to prevent you from acting out your dreams. One notable exception is that a lot of nightmares happen during deep sleep, and we are not sure why. If you experience nightmares or night terrors, they are for some reason um, often going to happen during deep sleep, and we're not sure of the reason for that. But normal dreaming seems to happen most often during REM sleep. The first REM cycle of the night typically occurs about 90 minutes in, again, on average, and REM lasts for about 90 minutes. And the first time you experience REM during the night typically lasts only about 10 minutes. And after REM, your brain kind of resets and it goes back to the beginning of the sleep cycle. After REM, you will go back into N1 and you'll be in this really shallow sleep. You can actually wake up very easily right after REM, and your brain will cycle back through the sleep cycle. But then, each time you experience REM during the same night, it will last longer. If you experience more than one REM cycle during the night, subsequent REM cycles might go as long as 1 hour. On average, if you have a standard night's sleep of, 6 to 8 hours, you will probably end up spending about 20 or so percent of it in REM. On average, adults spend about 20% of their sleep in REM. Children and infants have longer REM cycles than adults. Babies spend as much as 50% of their sleep in REM. Little kids spend a much higher percentage of their sleep in REM than adults do. We believe this is because dreaming is when your brain does a lot of memory consolidation and a lot of learning. And therefore, when you're really little, your brain has a lot more of that to do to basically learn and figure out the world. And therefore, that's what REM is for. We have discovered that people who are deprived of REM sleep, if you are awakened, for example, during your REM cycle and it's disrupted, or if you only take a little cat nap and you don't get to the REM cycle, the next time you get to sleep and you have undisturbed sleep, you will have longer REM cycles. And this is called REM rebound. People who are deprived of REM sleep for prolonged periods of time tend to have memory and emotional processing problems, which seems to be pretty solid evidence that that is a big part of what REM is for. In a typical night's sleep, on average, you will go through 3 to 4 REM cycles. As you get older, cycles shorten, but the need for sleep does not. You go through the whole cycle faster as you age, mostly because you're experiencing shorter periods of deep sleep, but your overall need for sleep does not decline. Children and adolescents absolutely need more sleep while their brain is developing. It is not weird that young kids and teenagers sleep for longer. And telling teenagers they're lazy because they need to sleep for longer periods of time is not fair or accurate. Their bodies literally need more. Their brains are developing. Now, speaking of this thing called dreaming, we are still not 100% sure what dreams are for. The function of dreaming is not clear. We believe that most dreams originate in the parietal lobe of the brain, because we know that injuries to the parietal lobe can cause people to stop dreaming. It has been proposed that dreams are a part of memory consolidation, basically the brain trying to figure out where current experiences fit in with past experience and knowledge, which is why we think that a lot of dreams involve basically details of your past suddenly being juxtaposed with current things happening. It's also believed dreams may be a way the brain processes thoughts and emotions. It's thought that dreams may be a way that the brain rehearses for day-to-day life and sort of practices experiences. It's thought that dreams might be a way that the brain gets rid of maladaptive thoughts and feelings. It's thought that dreams might be a way of the subconscious parts of the brain communicating with conscious parts of the brain, or a way that which the brain basically uh, continues processing and thinking about things while you are asleep and tries to communicate with you about it. We can say that most dreams last average of 10 to 25 minutes. Some little bits of fun trivia about dreams. About 10% of people dream in black and white. People who are blind and have always been blind will dream without visual. People who have had the sense of sight in the past and gone blind will continue dreaming visually after they go blind. People who have lost a sense will retain that sense in their dreams. Certain kinds of dreams are almost universal across cultures, and we do not know why this is, but almost universally across cultures, people will dream about flying, dream about falling, dream about running away from something and being in slow motion, dream about sex, dream about getting in car accidents, dream about failing a test, dream about dead relatives, and dream about their teeth falling out. That's an almost universal dream across cultures, and we do not know why. Okay, so enough about sleep. One other big area of cognition that I wanted to talk about. Let's talk about one of the most mysterious areas of the workings of the human brain. Let's talk about a thing called memory. Now, memory is not one phenomenon. Memory is a complicated phenomenon that I will say right now, much of it is poorly understood. Under the headings of memory, we put learning new information, we put the brain's ability to store and retrieve knowledge that has been obtained, and we put the ability to forget information, which is also important because the brain does not need to store indefinitely every piece of data you have ever experienced. I'm going to tell you right now that we do not have a good full understanding of how memory works. We cannot point to a specific part of the brain and say that there is the spot where your memories live. How the storage system for data works in the brain is not known. This is a mystery. There are several hypotheses that have been proposed. There are several models of memory that have been suggested. We know that certain regions of the brain are heavily involved in memory. We know the temporal lobe of the brain is heavily involved in encoding and storing memory and learning. We know that the hippocampus of the brain is involved in memory consolidation and transferring short-term memories to long-term memories. We know that the mammillary bodies are involved in recalling information, but as to how memory is drawn forth and recalled, as to how it is stored, much of this is not well understood. What we can say is we have been able to figure out kind of a model of how memory functions, even if the storage mechanisms are not well understood. Broadly speaking, we agree that there is a distinction between short-term memory and long-term memory. Short-term memory, also called active memory, or STM for short, is the aspect of memory dealing with fairly immediate or very recent experience. Only holds memory for a very brief period of time. We talk about short-term memory. That is primarily referring to very immediate experience. Only things from the past few seconds or the past few minutes. Your short-term memory is going to tell you about what I was just talking about immediately, might tell you about the things I was saying about sleep just a couple moments ago. That's all short-term memory. Now, there is an aspect of this that is a little bit further back that we call working memory. Working memory holds information in an active or short-term form for a slightly longer period of time for processing before it will either be discarded or encoded to long-term memory. Working memory is the aspect of short-term memory that deals with your most recent immediate experiences. Say the things that have happened to you for as long as you have been most recently conscious. So your working memory will be able to tell you, what did you have for breakfast this morning? Your working memory will tell you what happened to you an hour ago. Your working memory will tell you what happened to you before you sat down to listen to this lecture today. Recent past experience, not the immediate past experience, but things that have happened to you in the relatively recent past since you have been awake, let's just say. Now, when you are drawing upon past knowledge, what you are doing is you are digging into encoded long-term memory, and you are temporarily polishing it up and putting it back into working form for a short period of time. The more you do that, the more familiar that piece of information becomes to you. The more you work with a piece of information, the easier it is to work with. People sometimes say to me, wow, gosh, you know this information so well. You must be super smart. How do you know all that? I've been giving these same lessons every semester for 20 years. I dust off this chunk of memory very frequently, and therefore it is quite familiar to me. Now, long-term memory is indefinite storage. It can be explicit or implicit. Explicit memory, also called declarative memory, is your conscious, active recall of information. That can be further divided up into two kinds of information that we recall. We have episodic memory. Episodic memory is your memory of experiences. You remember your high school graduation. You remember that day you spent at Kennywood with your partner that you really enjoyed. You remember your sister's wedding. You remember a really fun party you went to last weekend. You remember the day your dad died. You remember specific experiences. Those are episodic memories. Or, under the heading of explicit or declarative memory, you can have semantic memory. Semantic memory is your memory of distinct facts. Semantic memory lets you know, oh, my anatomy professor's name is Mr. Davis. Semantic memory lets you know, oh, I live at 123 Johnson Street. Semantic memory lets you know the capital of Pennsylvania is Harrisburg. Semantic memory lets you know, oh, the bone of the arm is the humerus. Semantic memory is your ability to recall where you left your keys. Semantic memory is distinct nuggets of factual data. As far as we can tell, declarative memory is encoded by the hippocampus, that the hippocampus takes this data when you learn it and transfers it from short-term to long-term memory. And we believe it is stored by the temporal lobe of the brain. That is our best understanding. When you call upon this information, it is being taken from short-term memory to working memory. The more often you call upon it, the more familiar it is and the easier it becomes to recall. The less frequently you call upon it, the more difficult it becomes to recall. That's why it's easier to remember a piece of data that you use all the time, like, say, the password to your phone, uh, and it's less easy to recall a piece of data that you hardly ever use. Like maybe back in third grade, they had you learn the capitals of all the states, but it's been a long time since you had to know the capital of Kansas, and therefore that's not a piece of information that you remember easily. It should be reported, and this is important to know, that our brains are not good at sorting this out. Memories are tricky. Every time we dust off a memory to play with it, we are putting it back into working memory. We can build on it. We can enhance it. We can strengthen it. We can also mess with it. Memory is not static over time, folks. It can become fragile. It can become damaged. It can be modified. Do not think of your memory as being perfectly reliable over time. Because when we think back over memories, they get affected by our biases. They get affected by our experiences. Psychologists have clearly demonstrated this, that eyewitness accounts of crimes and so forth will be absolutely affected by what the witness thinks the person interrogating them wants to hear. And if people don't have good recollection of what they saw because it was dark and there was a big kerfluffle going on when the crime was happening, and then they get interrogated and the cop who's interrogating them wants more information, people's brains will fill in details and the person doing it will 100% believe that is what happened. And they will form memories around them. Our brains are good at making shit up and forming memories around that stuff. If you were happy with your ex while the relationship was going on, but then it went sour years later, and you think back on it, and you start thinking, oh yeah, it was never good at all, your memories of the happy times will be tainted. And you will start thinking of all the ways the happy times weren't all that good at all. And your memories can get messed up. And your bias can tarnish them. You can even find yourself creating memories where there were none. You all have family stories. You all have family folklore. You all have stories that get told over and over again at parties and so forth. It's the 4th of July weekend. Many of you are going to have family gatherings where old family stories are going to get dusted off and told. And there's this one story that gets told in my spouse's family about my spouse's uncle, who was at a party or a picnic or something, and somebody told a joke, and he laughed super hard at this joke and fell over at a picnic bench and spilled a bowl of potato salad all over himself, and just lay there on the grass laughing with potato salad all over his lap. And, people made fun of him for years about this. And, I remember telling this story to somebody else at another event, and talking about, Uncle Russ lying there on the grass, just laughing with potato salad all over his lap, that he was just, just so in the moment, he wasn't even thinking about it. He was just laughing and laughing there, lying on the ground with his shorts covered in potato salad. And I'm telling somebody else this story. And my spouse taps me on the arm and says to me, honey, you weren't there. Because I hadn't been there when that happened. But I had heard the story so many times that my brain had formed a memory of it. And I had completely forgotten. This was a thing that I hadn't been present for because you know how it is when you're with somebody for years and years and years. And I've been with my spouse for 27 years. And I'd forgotten that this was not a picnic I had been at. And yet I'd heard that family story so many times. My brain had just inserted it into my memories as if it had been one that I was there for. And I still have this memory in my head of Uncle Russ on the ground laughing at himself covered in potato salad that I wasn't there for. Memory is tricky. Be careful of that. All right. Now, I should also point out another thing about memory. What do we form memories of? We form memories around details. We form memories around data. We form memories around things that seem to us to have impact. A lot of times, the emotional impact of a thing is what we will form a memory around, like an event, like an object. And I know many of you are thinking, well, then why does my partner forget our anniversary? Your partner probably remembers the day you started dating or the day you got married. Do they remember the number? Do they remember the dates? Do they remember October 5th? Do they remember that? Because here's the thing. We tend to form memories around experiences. We form memories around significant places or around significant objects or around significant moments. We don't necessarily form them around things that are abstract. Things like dates, things like numbers, those tend to be abstract. They're harder to form memories around. So if your partner remembers that first date, but they don't remember what day of the week it was on, it doesn't mean it wasn't important to them. Now, there's another kind of memory that's not facts, that's not details. There's a kind of memory called implicit or procedural memory. Implicit or procedural memory is unconscious memory. It's not your conscious ability to recall specific facts or details. It's related to skills, habits, actions, and objects. Implicit or procedural memory is what we sometimes call muscle memory. It's your memory of how to do things. It's your memory of things like how to type, because you don't have to think about where to put your fingers on the keyboard or on your phone. It's your memory of how to use your toothbrush. It's your memory of how to take the steps when you walk. It's your memory of how to execute the movements needed to start your car, shift the gears, and pull it out of the driveway. You don't have to stop and think about every individual step because you've internalized all of those steps. Think about a little kid. You ever watched a baby learning how to walk? Watch the intense concentration on that little kid's face as that little toddler is focusing on every single step because they're having to think in that moment about every muscular movement and action and every plant of the foot as they're learning every careful step and every shift of the muscle needed to do a thing that they're doing for the first time. But you don't have to do that anymore. You've internalized it. That's procedural memory. You've committed that sequence of bodily actions to an unconscious memory. You don't have to stop and think about every little movement involved in brushing your teeth. You don't have to stop and think about every little action or movement involved in driving your car or playing a video game or whatever other sequence of movements you carry out to execute the things you do in day-to-day life. The skills you execute, the daily habits you perform. Those are all procedural memories. Other things that are procedural memories are things that are things like, okay, when you're reading, you don't have to think about decoding every word. You don't have to think about the sound that goes with each letter of the alphabet. You don't have to think about what each number individually means. You've encoded that information. You don't have to think about when you see a series of um, shapes lined up, like little kids playing a game in kindergarten, and they ask them, okay, what do these things all have in common? It's like, oh, all of them are triangles, or oh, all of them are blue or whatever. Pattern recognition is procedural memory. Distinguishing between categories of data and being able to say, oh, if I have a dog and a camel and a sheep and a rabbit all together, and you look at all those things and say, oh, all of those are animals. That's procedural memory. You recognize a category. That's a thing that you can tell. Procedural memory is also what happens when your brain uses one piece of data to recognize another piece of data. That's called priming. When you have a rhyme, like whenever you use memory tricks to remember one thing or another thing, like if you ever used a little rhyme in school, like I before E except after C, that is priming. That is procedural memory because you're using one thing to link you to another thing. Whenever you link two pieces of information together, that's priming. That's procedural memory. All these kind of back end kinds of learning you don't have to think about is procedural memory. Procedural memory seems to function in our brains in a different way. As far as we can tell, it is coded by the basal nuclei, the basal ganglia, as we sometimes call them, the masses of gray matter located down deep inside the cerebrum. And we think that it is stored in the parietal and occipital lobes. Now, what happens when memory fails? There are a couple of ways memory can fail. You've all heard of amnesia. Amnesia is a partial failure of memory, typically as a result of trauma or disease. There are two forms of amnesia. When most people think of amnesia, they're thinking of the Hollywood version of amnesia, retrograde amnesia, which is loss of past information, typically explicit rather than procedural. You all know the classic version of this. You get whacked on the head and suddenly you forget who you were or where you came from, like in the movies. And honestly, that's not usually how it goes. When somebody experiences retrograde amnesia, they don't usually experience a complete obliteration of their identity, and they don't usually completely forget who they were and where they came from. Normally, retrograde amnesia is going to be you get an injury or something, and you experience the loss of a chunk of memory. It's like, okay, I don't remember what happened to me associated with a chunk of time around the injury or the trauma. Or I've lost access to a chunk of memory around X chunk of years of my life, or X chunk of months of my life, or whatever. Normally it is not complete obliteration of identity. Once in a while, it's more severe, and it is. And people end up having to try to reconstruct their lives. And those are the more severe cases. Unfortunately, it's not usually like it ends up going in Hollywood either. where you know that in the Hollywood version of this, people are going around trying to figure out who they are and where they came from until the moment whenever they get some experience that jogs their memory, some loved one says some key phrase to them or shows them some meaningful object from their past or whatever, and suddenly that unlocks their memories and it all comes flooding back. Unfortunately, in real life, it usually doesn't work that way. And people who have had this kind of traumatic amnesia normally have to rebuild their lives from scratch. Now, the other kind of amnesia is weirder, and that is a thing called anterograde amnesia. Anterograde amnesia is the inability to form new long-term memories following the trauma. Normally, this involves a brain injury that damages the hippocampus. And basically, what's happened is that because of that injury to the brain, you have lost the ability to transfer data from short-term memory to long-term memory. And as a result, you're kind of stuck memories. And your brain will no longer store new memories for you. Every day is a new blank slate for you. All the things you experience today will be wiped clean when you go to sleep, and you will not store them. Some folks with this information find that if they do the same thing over and over again, after a long time, little bits of it start to encode. But for the most part, every new day is a clean slate, and all the data from the previous day is wiped clean the next time they sleep. Folks with anterograde amnesia basically are stuck in time. They live by leaving notes for themselves. And that means that most days, the first thing that they will experience is reading a note that they left for themselves that says, you have anterograde amnesia. Everything that you experience today, you will forget by the start of the next day. Write down anything that is important. Honestly, that one kind of terrifies me. There is a supposedly funny movie about this, an Adam Sandler movie called 50 First Dates, which I think is kind of gross because he ends up marrying the girl, and I don't like that at all. If you want a better movie about the experience of somebody with anterograde amnesia trying to reconstruct their life and figure out what happened to themselves, there's an older movie called Memento that is seen through the eyes of a person with anterograde amnesia trying to reconstruct how they got that way. And it's a really, really cool movie. I highly recommend it. It's a Christopher Nolan movie from about 20 years ago. Now, can't talk about memory problems, of course, without talking about dementia. Dementia is not one condition, folks. Dementia is an umbrella term for a bunch of different conditions that all involve a decline in cognitive ability or memory over time. There are numerous types of dementia. Some of them are a consequence of traumatic brain injury. Some of them are a consequence of severe damage to the brain as a result of certain psychoactive drugs. They are not, I will point out, a result of getting older. Dementia is not an automatic consequence of age. You are not doomed to automatically experience it as you get older. Not everyone succumbs to dementia. Lots of folks who remain sharp and active well into old age, and if you want to remain sharp and active well into old age, things you can do. Regular exercise, physical exercise seems to help. Keeping your mind active seems to help. Stimulating your mind with new experiences seems to help. Things that challenge your mind, doing puzzles, exposing it to new mentally stimulating information, reading regularly, doing puzzles, doing things that keep your brain engaged, doing creative things that challenge your mind. All those things seem to make you less likely to experience dementia as you age. But it's not inevitable. However, some forms of dementia seem to be the result of pathology that no one has any control over. The most common form of dementia responsible for between 50 and 70% of documented cases, is, of course, Alzheimer's disease. Alzheimer's disease is a progressive form of dementia characterized by the degeneration of neurons in the brain. It is not only a loss of memory, but also a decline in cognitive function as a whole, the ability of the brain to engage in clear cognition. It is mostly seen in the elderly. Most cases of Alzheimer's do not hit until the mid to late 70s at the earliest. However, early onset forms of Alzheimer's can strike earlier. There are some tragic cases that hit even in people in their 40s. My all-time favorite author, the late great British author, Sir Terry Pratchett, succumbed to early onset Alzheimer's. We have, as of now, no cure for Alzheimer's. There have been some recent very exciting developments in drugs that seem to slow the progression of the condition. And there are a couple of very exciting treatments in the pipeline that, at least in mice and rats, seem to have some promise in slowing the progression of the condition and possibly reversing some of the damage, but nothing that is yet approved for humans. We're working on it. We might have some possible therapeutics in the next couple of years, but we're not there yet. Alzheimer's in particular seems to be associated with two very particular neurologic symptoms. One with the formation of so-called amyloid plaques, protein deposits on the surface of the brain, and the other one with the tangling of a specific type of long protein chain inside of neurons called tau proteins. We do not know if either of these is a symptom of the condition or a cause of the condition, but they are both evident in Alzheimer's patients. There is evidence to believe that the predisposition to develop Alzheimer's runs in families, that if you have a family history of Alzheimer's, you are more likely to develop it. We have, however, also found that Alzheimer's is more likely to develop in people with a history of traumatic brain injury, and it seems to be comorbid with people who have family histories of Parkinson's disease and a couple of other neurological disorders. So there seem to be some outside factors as well, and it seems to be less likely, again, in people who keep their minds active. So you definitely can do yourself a favor in trying to keep your mind active. It seems to be comorbid in people who have circulatory issues, so anything that's good for your heart seems to be good for your brain in this regard as well. So can't do yourself any harm by trying to not do those things that are good for your heart. Bad for your heart. Anything that's good for your heart is good for your body as a whole, and it seems to be good for the brain too. Okay, so this has been the remainder of our brain lesson. I hope you've all gained something from this. I will see you all in the future. Take care.